So the textbook is here. I have it um, on my recordings all the time. If somebody needs, I can again send a link. And we are on section 3.7. So in the last section of chapter 3. So page 162. To get there quicker, I recommend to go 100 and maybe 75, about 15 pages added to it. Actually, should get more, but pretty much where I needed to be. So in that section, we saw interesting formula, factorial symbol, right? So you just start at 4 in this case, if that's 4 factorial, and go down 4, 3, 2, 1, or use a scientific calculator to get there. We also saw a pair of interesting formulas, that so-called permutations, and that's what we worked on last time, as well as so-called combinations, permutations and combinations. So that's what we were trying to get used to a little bit last Wednesday, and now we're gonna do it again today. Well, today I'm gonna need to end this pretty soon because I have an appointment that I must not miss again. So I need to stop the class after doing a couple of exercises, but that I think be good enough for this part of the story, because next time we will start to discuss chapter 4, and that will be, well, utilizing the word combinations again. So first of all, let me refresh your memories on how we used calculators. So if I try to do exercise number 7, it says, excuse me, calculate combinations to choose 5 from 52. So what I'm going to do is go for the favorite scientific calculator. So you just start typing scientific. And the choice one in Desmos that will need to use functions to get to combination. So if you go combinations, and then I return back main menu 52, comma 5. So this is how we used to do it, and that's the way we can have this calculated using technology, because otherwise it would take a long time to utilize the formula, and this experience in factoring and because is not as needed, because this is something that should be really done using a calculator. In fact, in the future chapters, that's how they actually start to recommend to do it. So instead of having fun with arithmetic, we just gonna use a calculator from day 1 rather than from day 5 or something. So combinations. The other formula with section has a so-called permutation. So if I go back to functions and not to choose second selection on the last row, but the first selection, permutations, and also try to put 52, comma 5, that will be a definitely larger number, 311 million. So these numbers, of course, were related with some type of factorial thing, but again, I tried to describe that last time a little bit at the end of the class, but if somebody is interested, that definitely worth watching a recording of last lecture that I emailed to you last Wednesday. But again, for our class purposes, it's not as necessary. Just want to realize that number of combinations cares about not to have any order, so does not really care about order, so no order is important. But once you start to order things, you have more ways to permute selected 5 objects. That's where permutations come in, and they're related with numbers of way to permute 5 elements. So it'd be 5 for the first, 4 for the second, and so forth. So if you want to multiply by 5 factorial, if we go back to functions, actually multiplied by 5 and then functions give you factorial, you will get exact same numbers. So that's the relationship with starting to permute elements around. But in lots of cases, you don't need to do that. You don't care on ordering things, and that's what I will discuss today, how we produce so-called lottery winnings, for example, if you don't really care about the order. In fact, whenever you play in the lottery, let's say Massachusetts lottery, that says select out of 49 elements 6 winning numbers. How many selections you're gonna have possible if you were to select from 49 in a 6? How many ways to do that? And then they want you to calculate the probability, which is a fraction. So in exercise number 9, you're gonna need to produce a fraction or a probability to win. So I can put, let's say, win W in the parentheses. And to win means we need to guess exactly one winning selection. So it'd be just one possibility. I can win the lottery if I guess only 4 or 5 numbers. I still get something, some winning. Yes, but they, I guess, discussing the main price. So it's like only one out of total, and the total will be that number of combinations. So I put a C, and then in the parentheses, 49, choose 6, right? So that's total number of ways to make a selection. 49, choose 6, and only one winning possibility. Now, one may wonder why this is combinations. And the answer is when you're trying to win the lottery, let's say you have a grid, if you ever played the lottery, 7-Eleven or whatever place, you can go and get a ticket for the lottery for free, and you will see numbers that you need to make your selection from. So it's like 1, 2, 3, dot, 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 etc. And what you need is to highlight some of them. Let's say you decided to highlight element 2, then something else. And when you do this process of selecting, you're winning, hopefully winning selection out of this grid of numbers, just by highlighting some of them. You don't really care in which order you highlight. So after highlighting that one, you might decide to return back and highlight another one. And it doesn't really matter which order you take. And that's the point of story, that you don't care about the order of selection. And in that case, if you don't need to put this selection order, then you have combinations. Then you're working with this letter C is number of combinations. Because if order was important, then it would be different. Then it would be permutations, remember? So let's try to do that. So I'm gonna go to numbers and go 1 divided by, and then I will use combinations, so functions, right? And then combinations. And back to main. So for this particular case, we select out of 49, 6. And you say, what is this? Is that possible? What kind of selection this is? What number? What number did you produce? Well, this is power of -8, which means you need to move your decimal 8 places to the left in the negative direction. So if you move it once, decimal point here needs to be in front of 7, but then you need to move it 7 more times. So you need to place 7 zeros in front of this 7, 1, whatever, dot. So you need to fill the empty spots in front with zeros, just like that. And then you get a very, very small number. So you actually select 1 out of like 715 of what? Well, that's thousands, millions, billions. So is that really possible to guess out of billion possibilities? Well, the answer is no. Statistically, I know that some people say, no, Alex, there are 7 choices. There are still 7 possibilities out of whatever, billion. Well, if your probability is less than 1%, and that's 0.00 is way, way less than 1%. In statistics, people, it's not possible. So there is no chance that you're gonna select. And that's another thing to realize, that probability, which is less than 1% in statistics, assumed not to be possible to guess. So in general, for playing lottery, unless you have some other inside information, then your chances might increase, but otherwise, with chances less than 1%, no statistician in the right state of mind would recommend you to do that. So all of the lottery games go under the same structure. It's going to be selecting out of combinations because no order is important. So this story is combinations and permutations. So once you figured out if you have C for combination or P for permutations, well, then you know how to do the exercise. You just put this in a calculator. And that's the point of this whole story. So let me try another exercise, like problem number 17. And in this exercise, they talking about selecting a treatment group. So in exercise 17, they say pharmaceutical conducted a 6 people selection out of 15 volunteers. So from the set of 15, they decided to choose 6. And looks like they just give them some kind of medicine and see what's going to happen. And that's how it goes. So looks like we don't really care about the ordering of these volunteers because at the end of the day, they just all get the same thing. So out of 15, I choose 6, right? So I can use 15, 6 number of combinations to see all the possible selections. And again, it's combinations because I don't care about the order, right? because we don't really worry who eats this medicine first, who is the second. At the end of the day, they all will get the same dose of this medicine and will be studied then by the doctors, see what's happened after they consume that drug. So no order means combinations. That's the point. So they say, what's the probability that they selected 6 youngest people? Well, probability is P, which is always a fraction. And now they decided to select 6 youngest. So I can say 6 youngest. Why? 6 youngest people. So it turns out that there is only one possibility. The youngest people, if you arrange them in the order of age, will be the last 6, and there is only one way to choose the 6 youngest. You just take the last 6 people. The other way to put this is just say one choice out of this many combinations, 15,6. Someone could say, Alex, there are 6 youngest people, looks like, and out of them, we need to choose all 6. In other words, we go with selecting from 6, all of them, 6, and see how many selections will be there. So we don't care for order, this is combinations. And it turns out that this is equal to 1. I say, you sure? Well, put this in your calculator. It will, of course, show you the answer, so you can actually go and enter functions, right? Combinations, main, 6. So how many ways can you take all of them? Well, just one way, just take all of them, all 6. So it's 1 in that. So if you like, you can put it as combinations 6 choose 6, or you could just use 1 intuitively and then divide it again by that denominator that we have in our fraction 15, 6. You need to put divide. Put divide here. Okay. Now I need to put combinations a little bit more carefully. See, the nice part of this calculator, it shows you if you happen to mis-enter something, so you can all go back and fix it, right? So 1, 5, 6. Again, this is going to be a very small number. Notice there's negative power of 4 again. We're gonna need to move decimal 4 places. Okay, so I move it 1 place in front of 1, and then 3 more places. So it'd be 3 extra zeros that I have to have in front of my decimal point. So 3 zeros, and then I go 199. So that's just my answer. So no need to continue with this decimal, so just put that. Because again, there is no chance that this is going to happen. So if you were making this selection at random, no way this is possible, means that, well, looks like they deliberately selected youngest people in a group, and that's the point of their exercise. Was the probability no chance, which means that they not just selecting at random. So they probably selected the youngest or the strongest, probably people from their perspective, to see what happens. Do they consume the drug? And that they, well, anyways, as I said, I will stop at this stage. I need to really run for one place, and I will let you enjoy the rest of the day. So we will start with chapter 4 next time. That's the plan. And turns out that all problems here are about one main observation. Is that combination? Do we care about order or not really? And the only case we do care about order when we give more information. So once you selected 6 people, they say, okay, selected those 6 people, let's order them. Who's the older, who's the present, who's so we start to assign them positions. So you have extra information. And if you don't, it means it's combinations. Turns out combinations are everywhere pretty much. And that's what we're gonna utilize in the next chapter 4. And as I said, I don't wanna start doing it right now, so we'll continue. We're in a good shape covering the material, so I'm going to stop this little recording for today then. And you can enjoy the rest of the day. You deserve to have a little bit of a break, right? So I'm gonna stop this recording.